Okay, so the critical path method. The critical path is the longest path through a network diagram, and it determines the shortest time to complete the project. So in other words, the longest path is, you can't complete it any shorter than the longest path. And then float, which is also called slack, is calculated into a network diagram. So there are three types of float. There's the total float, or slack, which is the amount of time the scheduled activity can be delayed or extended from its early start date without delaying the project finish date or violating any other kind of schedule constraint. And we'll talk a lot more about this later. The free float is the amount of time that a scheduled activity can be delayed without delaying the early start date of any successor or violating a schedule constraint. So that's just the task adjacent to it. And then the independent float, or slack, is the amount of time an activity can be delayed if all the immediate predecessors finish at their latest finish dates and all the immediate successors are to be started on the earliest possible start one. So in other words, this is another place that you might want to write down things for your brain dump.
The total float, okay. From the early start date without delaying project finish date. I feel like a doctor at times with all the terminology.
Yeah, I was going to say, and you know, terminology specific for this 4-hour test session. Tell me when you're ready to go on.
So here's my question on this. So really, on a test, what would you look for to differentiate between these? Would the total float be just the slack where it can be delayed without delaying a project's finish date, you know, extended from its early start date? Then the free float would be dealing with the successor. And then the independent would be the immediate predecessor. So whatever took place before it, I mean, what would be the trigger points that you would remember it?
Well, the way you'd calculate that, obviously you'd have to have a network diagram and you'd have to understand the critical path. And sometimes the total float and the free float could be coincident. But the total float just means that you can move a task that's, and you know, generally not on the critical path, because if it's on the critical path, it has no float or slack. The amount of time that you can move it so that you basically don't push out the end date. Whereas the free float is just moving that task between its two adjacent tasks. So you might be able to move a task way out, and then it causes everybody after it to start late. But
so on the free float, if you could have two tasks within the same period of time, but you could start one before the other. Would that fall into a free float?
Well, I think what they're really looking at is that if you started a task that was dependent on the next task, you know, you don't want to push the next task. But in the total float, you could push the next task as long as then that task didn't push into something that changed the endpoint. So it's all about the endpoint in the total float, and it's just about the adjacent tasks in the free float.
As long as it doesn't impact the adjacent task.
Right. So the overall. Okay, so we're going to calculate the float, and basically the total float, and it's probably better to see the next chart first. Okay, so in the forward pass through a network diagram, we're going to calculate the early start, and then usually right here is where I'd put the duration. You know, so the early start plus the duration equals the early finish. And then you're going to come back and do a backward, and then that's, you know, that early finish is going to be the start for the next task. And likewise, you're going to go back through the backward pass, and then whatever comes from the previous task is going to be your late finish, then minus the duration is going to be your late start. So going back to this chart, you need to identify the critical paths through the network, and then you do the forward pass to find the early starts and the early finishes, and then you calculate the late start and the late finishes by going backwards. So, and speaking of backwards, you know, the next chart after next is even more expressive. So again, make sure you understand the total float formula.
Equals late. So this is an actual formula. Late
Well,
start
minus early start. So the total float for a task is either the late start minus the early start, or the late finish minus the early finish, as depicted in this diagram. So it's either late start minus the early start, or the late finish minus the early finish. And both of them should, the answer should be the same. You know, if you, in other words, if you've done a network diagram and you do this minus that, and you do this minus that, and it's not the same number, then you've got a mathematical problem, you know, with your small number math on the test. So let's go to the critical path example and look at how this is calculated. So basically you start at time 0, and activity 1 has a duration of 3, which is not adequately notated, but say it's 3 because you're going to finish on day 3. Okay, so this is the early start, that's the early finish. So then from activity 1 you go to activity 2, which starts on day 3, because you're just going to pull that straight over. And then activity 2 also has a duration. Oh, there the duration. So that has a duration of 3. So, and I like to have the duration right there where my hand is. So 3 plus 3 is 6.
So it ends on the 6th day?
Huh?
Is that, so it has a duration of 3, it ends on the 6th day.
Uh-huh. And so then that carries across to day 6, to activity 4. And again, you know, we're assuming all these are finished to start because there's no other indication on the arrows. So activity 4 has a duration of 4. No, what are we looking at? Okay, activity 4 has a duration of 8, so 6 plus 8 is 14. And then
I was going to say something's not right there. Okay.
No, it's okay, because this is activity 4. Down here is activity 3. So before we go to activity 5, because activity 5 needs both activity 3 and activity 4. So activity 1 ends on 3. So the 3 goes over here. It has a duration of 4, so 3 plus 4 is 7, and then it feeds into activity 5. So now on the forward pass, you're going to take the biggest number between 7 and 14, so obviously that's 14. Activity 5 has a 4-day duration, so 14 plus 4 is 18, so that's where you're going to end at 18. So 18 drops down to here, because it just does. And then we know the activity has a duration of 4, so 18 minus 4 is 14. And then that 14 gets translated back to here and to here. And then 14 minus activity 4's duration of 8 is 6. And here we have 14 minus activity 3 duration of 4 is 10. So you see where these numbers are coming from? And so...
yes.
So both 3 and 2 feed into 1, so we're not going to do that yet. Okay, so 14 minus 8 is 6, and then the 6 goes back here. 6 minus 3 is 3. So between 3 and 10, now this on the backward pass, the smallest number goes back into the late finish. So here we're going to pick 3, and then 3 minus 3 is 0. And so you know you've done it right when at least one of your paths ends up with 0. If you don't end up with 0, then you got a mathematical problem somewhere.
Okay.
And so you can see that everywhere where the float, 3 minus 3 is 0, 0 minus 0 is 0. 6 minus 6, 3 minus 3 is 0.
Start at 0. That's the bottom.
So every place, where the late finish minus the early finish equals the late start minus the early start. So those are all float zeros. So that's the critical path, because that is 18, whatever the units are, through the thing. Whereas, this would be 3 and 4 and 4.
So this
if we
up is the forward. This other looks like it's a back process. This activity 3. So
well, activity 3 just has has the float of 7, because 14 minus 7 is 7, and 10 minus 3 is 7. So activity 3 could start as early as day 3 or as late as day 10 and not push the end date.
Okay, all right, I see. Okay.
Well,
I'm telling you, I feel like I'm fried mentally. I'm mentally fried.
Well, good, because we'll end at not good that you're mentally fried, but we will end at the end of this discussion, and then hopefully you'll sleep on it, your brain will solidify all this knowledge, and then we'll get back at it tomorrow. And I'll give you, if you would like, I'll give you some extra work on terms of network diagrams, because you really will have to do these quickly. And the thing that you're going to get is maybe something like this.
Extra work on the network. If you can give me some extra stuff and samples on the network diagrams, it would be perfect. I mean, I see this and I'm looking at it, I'm like, oh, I mean, it makes sense.
Uh-huh.
But I feel like I'm mentally burnt at this stage.
Well, and you definitely do need to practice these and be fast, because, in other words, there will probably be, like I said, 5 questions on this diagram, but it's still going to take you probably more than 10 minutes to, look at the table, draw the picture, read the questions, because they might say, okay, what is the float on activity 3? Okay, so then then your answer is 7. Or they might say, what is the late start for activity 4? And so then you say 14. Or they might say, what is the early start for activity 2? So you could say 3, but another, you had to draw the whole diagram and do the forward and the backward pass before you could do that.
Oh, okay.
So
this is slide 279.
Yes, it is.
Okay, so I have to look at and just read it over and get, familiar with these again. It's been a long time. And is a longer critical path. 1, 2, 4, and 5. 1, 2, 4, and 5. Okay. All right, I'll have to work on those. So whatever you can.
It's definitely something, and you can be assured that you will get, at least a set of 5 questions. And I don't think you really want to just miss all those.
No.
Okay, now we're going to talk a little bit about schedule compression, and then we're going to have an example. So there's basically 2 ways to compress a schedule, and one is fast tracking. So if you normally had an A, B, C schedule, you could do A and then do B and C in parallel. And so the good thing about that is then it gets done at the end of whichever of the 2 is longer, and you don't have to wait for B to finish for C to happen. But if this is like sheetrock, painting, carpeting, the problem of doing painting and carpeting at the same time is, or, relatively at the same time, A, you're trying to occupy the same space to maybe paint and carpet the same room, but B, you might spill some of the paint on the carpet where it wouldn't matter if you spilled some of the paint on the bare floor. So fast tracking can be good, and it can reduce cycle time, but it can also have, you can also, to coin a pun, paint your way into the corner. Okay, crashing involves adding more resources to get the job done, but sometimes the problem with crashing is you can't put 9 women on a baby for a month each and end up with a baby at the other end. So not everything can be fast-tracked or fast-tracked successfully, and not everything can be crashed. But these are 2 kinds of schedule compression methods that you will be expected to understand the difference between and the definition of on the test. So here's an example of schedule compression. So, for instance, activity A has original duration of 10, and you could crash it in days to 8 to save 2 days. And if you look at the original cost in dollars, the crash cost, the extra cost, and the crash cost per day, and it's too bad that we have the answer down at the bottom of the page, because basically the issue is, which one would you pick? And basically you want to pick the one with the minimum crash cost per day. So this is another one of those things where you might want to put into your brain dump, pick the activity with the minimum crash cost per day. And so you can see how that's calculated in terms of, the original cost in dollars, and then the crash cost. Obviously, the extra cost is 2,000, and then divided by the 2 days is 1,000.
2 days.
Yeah, whereas this one, you've got the extra cost is 10,000 divided by 4, 2,500. 2,000 is, just you get 1 day for 2,000, and here you save 2 days for 3,000. So if you wanted to reduce your schedule by 1 day, you've got to look for the one that does it at the least cost.
Okay.
Okay, so here's some impacts of schedule compression. So if you fast track things, that adds risks, and obviously that increases management time for the project manager, because you've got to figure out what all the risks are and what the mitigations are, and whether or not you really want to do that. Okay, and crashing obviously adds cost and increases management time for the project manager, because as we'll see in communication, the more people you put on a task, the more communication channels you have, so the more complex and necessary it gets. Okay, another way you can reduce or compress the schedule is to reduce the scope. So you can save both time and cost, because remember we were talking about our iron triangle of scope, time, and cost. But the problem is you're potentially going to take on some customer dissatisfaction, because when you take something out of the scope, that was potentially something somebody was interested in having. You can cut the quality or the conformance to the requirements, which potentially saves cost and resources, but again, it increases risk. And then you can reallocate the resources, maybe putting a better, faster, smarter engineer on a task, and trying to do that in a way that doesn't add cost or increase risk. But generally it's going to do one or the other, because if you change horses, as it were, and put a better engineer on that task, then you would think they would necessarily be charged at a higher rate. And or putting somebody on the task that wasn't originally on it, so maybe hasn't been following it through risks and requirements and design and whatever, and they're just getting it for implementation, could potentially cause, some problems to happen. So here's some other kinds of scheduling techniques. We talked a little bit about the what-if scenario. And, so what if a particular scenario changed on the project, and, would this produce a shorter schedule? So, again, looking at our assumptions and constraints might give us some what-if opportunities to say, well, if we could force this to happen, we could shorten up the schedule. Again, we could use the Monte Carlo analysis. Again, you don't have to ever perform a Monte Carlo analysis on the test, but you'd have to know what the Monte Carlo analysis is. And this is computer modeling. Again, you've got to have a whole lot of data to make the program work. And you can simulate the various outcomes of a project by having different input variables selected, and then they, problems and concerns pop up at random, and you can see kind of the probability distribution of the likelihood of finishing on time or optimistically or pessimistically. And then a resource optimization technique, and this is using a stable number of resources by leveling their efforts. So I was talking about, you know, not using Charlie Brown shirt. You know what I mean when I say Charlie Brown shirt, right? I once said that into a room full of Asian students, and they looked at me like, no, we have no earthly idea. But basically, you don't want to necessarily increase staffing and then decrease staffing and then increase staffing and then decrease staffing. It would be better to have a flat level of staff so that you don't have people coming and going and, you know, being brought onto the project and having going away parties.
They keep it consistent.
Right. And, you know, then you don't bring in people who don't know anything, and then you don't let go of people who maybe are the only ones who know some key fact. And then there's the critical chain method, and that's where you might put some delays in the schedule, but you put them in such a way that nobody thinks, ooh, I'm going to take up that delay, and you know, just cool my heels or kick back, or say in a, you know, in a matrixed organization, oh, I'm going to go work on another project that has a hotter fire, because now I know that there's some slack built into this critical chain. Okay, so the last thing we're going to do, and isn't that always good to hear last, the last process we're going to have in scheduling, and you know, you said we had 45 more minutes, and, you know, I didn't annotate the time, so I'm hoping you have time to finish this section. Is that okay?
Is this our last one?
Well, this is our last process. We got a few more slides. You know, we got the quiz and stuff. But we're done. You know, we're done with the talking part of this thing in just 3 more slides. So control schedule, obviously in the monitoring control process group. The control schedule is the process of monitoring the status of project activities to update the project progress and manage changes to the schedule baseline to achieve the plan. So it's obviously part of monitoring and controlling because it has control in its name. So here we're going to use the project management plan, the documents, the work performance data, and the organizational process assets. And then to control the schedule, we're going to analyze data. We're going to use our project management information system, which is where we're storing all of this data and information. We're going to calculate our leads and lags. We're going to understand the critical path method. We're going to optimize our resources and potentially apply some method of schedule compression to control the schedule. And out of that is going to come work performance information. Remember, we started with data, and we're going to do analysis and make it into information. We're going to come up with schedule forecasts. We're going to come up with some change requests, as well as potential updates to the project management plan and the project documents. Okay, so here's a business scenario. Try this one out for size.
Let's see. One of Genesis is reporting. How she can get the schedule. How can Janice go about solving the schedule problem? Well, wouldn't we do a what-if scenario?
We could potentially do that.
I mean, I would definitely do a what-if scenario. I'd look at all my project activities. You know, I want to look at all my project activities. I want to understand. I'd probably use, I'm just trying to think, Genesis Fair, how she can get what if. I definitely use a what if scenario for this.
Okay.
I would want to determine my activities at what rate they're flowing in a matter of where are we falling behind as far as tasks. I don't think I can think anymore.
Okay. Well, here is the answer. So basically, using the team's assessment, the team needs to know the critical path, so they need to understand what that is, and then understand what can be rearranged to crash and what can be rearranged to be parallelized. And so by using these schedule compression techniques, and I don't know how you'd know the number 95, but Janice could increase the project's productivity rate to 95%. So that must have meant all went well in terms of crashing and parallelizing tasks.